All right, hello everybody. Welcome back to Math Background for Machine Learning. So today we're going to do in lecture basically a bunch of examples and little exercises that are intended to help everybody with areas that seem to have been causing difficulty for a lot of people. So I hope you find all of these helpful, and let's get started. So we're going to start with an extended example of using Bayes' rule. So you've seen Bayes' rule a bunch of times already, and there's this common pattern that you'll see where we maintain some distribution P of I'll call it P of state. Right? And so what'll happen is that you'll have some random variable that can be in a bunch of discrete states, 1, 2, 3, 4, 5, and you'll have a probability distribution over which of these states are likely, right? So this is my cartoon of a probability distribution, right? And so the state can be any variable that you're interested in. It could be, for example, whether Alice is up to date or not in the homework exercise. It could be what the die roll is that your friend saw, but you didn't because it was under the table. Those were a couple of examples of different types of state. We use state just as sort of a generic phrase to describe any random variable that you're sort of keeping track of for a while. And all right, so you have this state, and it's initialized in some known probability distribution. And so here's, let's say this is the initial value. And the first thing that you need to do is you get an observation, right? So you have some, this is the initial P of state. And then we have some model, P of observation given state, like that. And so we'll call this, like I said, the observation model. Right, and so that's going to be, well, we can make another graph. And it's going to say, for each observation, so here an observation could be something like your friend said that the die was even, or you measured some physical quantity like the length of a sample and got 23.2 centimeters, right? So it's some observation you can make. And for each observation, again, we can make a graph over states. So 1, 2, 3, 4, 5. These are the values of the latent state. And there'll be, let's say that your observation is something simple, that it could be any one of the first 3 states, and it is not one of the latter 2 states, right? So this here, right, this sums to 1 because it's a probability distribution. This is here, right, we're varying the variable state across here, and because the state appears on the right of the conditioning bar, this is not a probability distribution here, right? So this is the, for any given state, if we varied observation, it would be a probability distribution. But here we're holding the observation fixed to whatever observation we actually got, and we're varying state, right? And so this whole thing, P of observation given state, right, that's what's on the y-axis, and the state itself is on the x-axis here. Right? So again, this here is a probability distribution, this is not, right? And so Bayes' rule says that our new state is proportional to the original P of state, right? So our new state is P of state given observation, right? And so that's proportional to P of state times P of observation given state, right? And it's proportional to that, so I'm just going to write divided by our favorite normalizing constant eta, right? And so to get that, what we do is we just multiply these two things by one another, right? And so we'll get here, again, it's going to be a graph over possible values of the state. And so here, these are going to be essentially 0, right? And so in the end, we'll get essentially 0 for states 4 and 5. And then these guys, they're all multiplied by the same thing and then renormalized. And so we're going to get the same relative sizes of these 3 bars, but because we're normalizing, we're going to make them each bigger, right? Because we took away some probability mass over here, and so we'll normalize, make them each bigger, and it'll look something like this, right? Okay, and so what we've got here then is a pattern for using Bayes' rule where we start out with some information, which I'm calling the initial information, P of state. We get some new information through an observation, and that observation is probable in some states and not very probable in other states. Then we incorporate that information to get a new state. This new state is often called your posterior distribution, and your initial state is often called your prior distribution. And so we'll sometimes use that terminology. And the way you get your new state, your posterior, is you use Bayes' rule, right? P of state given observation is proportional to P of observation given state times P of state, right? And then here's the proportionality constant. And qualitatively, what's happened is that the values of state for which the observation was probable, well, those values of state become more probable. And the values of state for which the observation was not very probable, those values become less probable, right? So this pattern of prior observation or evidence and posterior, this comes up over and over again in machine learning. And so what I wanted to do, I wrote out a code example that we're going to go through now that shows how to do this over and over again, just like you were doing in the Alice and Bob example for the homework, right? So in the Alice and Bob example, there was a number of weeks, one after the other. Before each week, you had a prior before that week. During that week, you got evidence. And at the end of the week, after seeing the evidence, you had a posterior, right? And we asked you to track that posterior over a number of weeks. That pattern, by the way, is called a hidden Markov model, where you have the same model every week for a number of weeks, one after the other. You don't need to know that name. All you need to know is that it's basically a bunch of applications of Bayes' rule. So I should say, by the way, that in between this kind of application of Bayes' rule, it's pretty often to have some kind of process that scrambles up your state in some way. That's usually called a transition. And so in the homework with Alice and Bob, the transition was in each week Alice had a probability of catching up and a probability of falling behind. And so our longer example is going to have that too. So let's go now and take a look at this example. So, all right, here is the code that we're going to be going through. I'm going to make that bigger. Oh man. All right, I don't see, if anybody remembers where the Zoom menu is on MATLAB, please let me know. Otherwise, I have posted this code on Piazza, and so maybe you guys can look at it there. Yeah, that doesn't seem to help. All right, I apologize for the text size. All right, so in this, let's follow along. If everybody could just download the code from Piazza. Actually, you know what I'm going to do? I'm going to paste this code into another application and magnify it there. All right, this looks like it's going to be better. There we go. Oh, somebody suggested Windows Zoom. Unfortunately, that doesn't work. Windows Zoom just makes the window bigger, not the text inside the window. So we're going to go with this copy-pasted version, and hopefully this will be enough for everybody to follow along. All right, so let's start out here with build transition matrix. So this piece of code is actually kind of complicated. So rather than going through exactly what it does, I'm just going to show you what it does. So what it does is it builds this matrix, right? So what we have here, this example is going to have 100 possible values of the state. And in those 100 values, there, this will work. All right, so in those 100 values, every iteration, every time we do a transition, there's going to be a probability for every state that we're currently in. That's called the from state index. And then for every state that we could go to, that's called the to state index, we're going to have a probability of making that transition. So for example, if we're in state 10, we can read across this heat map to get the probability of showing up in any other state. And you can see here, it looks like we're likely to end up in about state 14, let's say, right? And there's some chance of ending up in state 13 or 15. Right? So what's happening here, you can think of the states as being arranged in a giant circle, and every time you do a transition, you move forward a few indexes around that circle, right? And then down here you can see that you wrap around to the beginning once you fall off the end of the highest index, right? All right, so this here, right? This is in our example. This is the probability of the state in week 2, given what you know about the state in week 1. All right. So given that information, I can just generate a sequence of states. So what I've done here is I've plotted again across all of the possible. Right, I've gone 300 steps. So this is like 300 weeks in the Alice and Bob example. I've plotted what that state index actually is, right? So when we're using this sort of model, we don't actually know this, but because this is an example, I can generate some data from this model just so that you can see what that data looks like. And you can see that, like I said, you're sort of going up and up and up in state index and then wrapping around to the bottom when you fall off the top, right? And it looks like each cycle takes about 30 steps. All right, so now what you do get is observations. And so what I've done here, I've made a plot, and so the way to read this plot, we're going to have a two-dimensional observation. The observation, you can think of it as being discrete with a very fine number of bins, or if you're comfortable with continuous probability distributions, you can think of it as being continuous. But what we've done is we've noisily observed our position around the circle, right? So we have, a circle that we're going around and around and around like this, and let's say we start here and we noisily observe our position. So we get, a discrete one of the bins somewhere near what our actual position is, and then we move forward to the next week and we get another noisy observation of where our position is, and then another noisy observation, and then another one, and then another one, and so forth. Okay? So this is the sort of data that's generated from this model if we just sample from the model. And now suppose that we have that, that sort of data. What we could do is we could try and back out what were the latent states at any given time. And so in order to do that, we have to get, when we can do this iteratively, starting at the beginning of time and moving forward. And what we can do is, just like in the example, we can get a probability distribution of where the what the latent state is at any given time step by applying the transition probability distribution to the previous time step. And then we can get an observation likelihood. And the observation likelihood is probability of the observation we actually saw for every possible state. And so here is a plot of the observation likelihoods, right? And so the way this plot is, again, a heat map. And the way to interpret it is, so for example, at week 100, right, we just go upward and we find here, right, here's the brighter colors in this column of the plot. And so what this is saying the observation that we actually got, it's likely to have happened in state 20, for example, a bit less likely to have happened in state 25, and if you go up to state 40, it's almost certain not to have happened, right? And so you can get, again, the observation likelihoods. I've made a color scale here for the heat map. So black means 0 probability, and up here means high probability. And again, these are not normalized to form a probability distribution. In fact, their normalization doesn't really matter. All right? And so now, given this information, let's scroll down in the code, right? I generated the observations. I plotted the observation likelihoods. And here, this is the code that I want you guys to take a look at under this section called forward pass. So what I'm going to do is, in this variable called alphas, I'm going to, so I'm pre-allocating it here. It's an array that's n, the number of hidden states, by steps, the number of time steps. And I'm going to fill in each one of these, the columns of this array, I'm going to fill in the posterior probability of being in a particular state at a particular step. So remember, the states are discrete steps around the circle, and so this is going to be a probability distribution for where we are around the circle at each step. And so we can initialize. So this would maybe be even more clear if I wrote, so alphas of :1, that's MATLAB notation for the first comma of the array, first column of the array. And I can set that to be our prior distribution, which is to say 1s of n1, divided by n, right? That's the array that's 1 over n in every entry. And then I can say, right, component-wise multiply our current probability by the observation likelihoods in that column, right? And so the uniform assumption goes there. And I've messed up the formatting here, so let me fix it, right? And so here I've computed this z, which is the normalizing constant, and I've divided each one of the probabilities by that normalizing constant, right? So I've made that column of the array sum to 1. And now I'm actually going to accumulate the log of the normalizing constants. Oh, sorry, I'm getting a question. Do people need to install MATLAB for today's lecture? No, you definitely do not need to install MATLAB for today's lecture. If you don't have MATLAB installed, that would be more than, potentially more than an hour and a half proposition to install it. I'm using MATLAB because that's something I'm comfortable with in order to show you this, this example. In the future, MATLAB is a fine piece of software, and if you like it, you're welcome to install it and use it to play with the code. There's also an open source alternative to MATLAB called Octave, and that's also recommended because MATLAB itself is kind of expensive unless you have access to it through CMU. So no need to install MATLAB. In general, with all of these software tools, use whatever software tool is comfortable for you to accomplish the job at hand. And we are, if you're working with somebody or if you're submitting a homework assignment, we'll try and make the software tool be one that's not so hard to work with. But in general, if you're just showing an example to someone, use whatever software tool is fastest for you to construct that example. All right. So, so I'm going through this code in some detail so that you can see sort of a more extended example of how you might actually use something like this to calculate probabilities for a machine learning problem. And so what I've done is, so for the first step, I have gone ahead and computed the posterior probability distribution. And so now what I'm going to do is iterate over all of the remaining steps. And here, this part, I'm taking the probability distribution at the previous step and multiplying by the transition matrix. And that will calculate the probability before any observation of arriving at the current, at each state in the current step. And then I'm component-wise multiplying it by the observation likelihoods. And again, I'm calculating the normalizing constant, dividing by the normalizing constant, and accumulating the log normalizing constant. All right? And so when I do this, let me now run this section of code that we just looked at, right? And it looks like this. And you can see that if we go back and forth and plot the observation likelihoods and now the probabilities at each time step, right? What has happened is that it's gotten a heck of a lot smoother, right? Because now these observation likelihoods, they only say anything about the observation you got at a particular step. They don't have any information about where you might have been at the previous step. Whereas now, if we use Bayes' rule recursively forward in time, we'll find out that, well, there's some set of states that we're likely to be in based on what we knew at the previous time step. And we can combine that information with the observation likelihoods to get a much better idea of where we actually are, right? And now what I'm going to do is I'm going to go and I'm going to replot the actual sequence of states that I used to generate this data. And remember, in the real world, we wouldn't know this, but it's good to compare, right? So these little blue X's are the actual states that I used to generate the data. And you can see that to a fairly high degree, they match the areas that we thought were high probability when we did Bayes' rule. And so it's always comforting to see that math works right? That Bayes' rule actually successfully told us where the state was likely to be. And when we plotted where it actually was, it lined up with that. All right. And so that's all I wanted to say about this example. Please feel free to keep asking questions about it on Piazza or directly to the TAs. And if there's a common question, I can try and answer it later on in the lecture. And just as a reminder, this code is posted on Piazza, so you can look at it in more detail and ask questions about it later if you like. All right, so let's go back now to our slides. Actually, let's not go back to our slides. What I want to do now is go through the lecture notes that I posted before class today. And these are not, you are not required to have read these already, but I want to use the images that I prepared in order to lecture about it. This is a fairly short set of lecture notes, so we'll just go through it and answer questions about it if people have them. So the first thing that I want to do is describe what's called a contour plot. And so contour plots are, if you've been hiking, you may be familiar with them already. What they show is position on the x and y axes, and then the height is shown by the colors and the contours. And so what's happening here is each one of these contours is also called a level set or an isoline. It's a set of this form, right? It's a set of the form x such that f of x. Oh, going back to the example, people are asking what eta is. So let's go back to the slide here. So here, right, eta has two interpretations, right? It's the normalizing constant that you use so that this distribution sums to 1 is actually a probability distribution. So I'll just write sums to 1. And this one does not. Right? So eta here, this is the normalizing constant that makes this sum to 1 as a probability distribution. And it also has an interpretation. It turns out to be equal to the marginal probability of the observation that you actually saw, right? And so there's, this is the two interpretations of Bayes' rule, right? There's the version of Bayes' rule where you know P of obs ahead of time and you just use it. And then there's the version where you don't know it and you get it from the fact that the probability distribution has to sum to 1. All right. So hopefully that, that explains eta. And we'll go back now to this. Okay, so here, here's an example of a contour plot, right? And so this is a function where the deepest valleys, like this one right here, are somewhere around a height of minus 0.15. You can tell that by matching with the color scale here. And the highest mountains, the highest peaks, are around 0.25. Again, you can tell by matching with the color scale here. And then each one of these lines, it's called a contour or a level set. It's a set of this form right here, where the height of the function is equal at all points on the level set. And so these are a useful way to be able to display a function. And in particular, this function here happens to be the nonlinear discriminant function that we learned in last lecture. So on top of the contour plots, I've plotted the cross class and the circle class. And so you can see that positive values of the discriminant function, highly positive values of the discriminant function, are over here where there's a lot of circles, and highly negative values are over here where there's a lot of crosses, which is what you would like in a discriminant function. The other thing is that there's a special level set for the discriminant function, which is to say the zero level set. I've drawn it with a thicker line here, right? And this zero level set is exactly the boundary between the two classes. Over here, on this side of the thick line, we say that it's the cross class, and over here on that side, we say that it's the circle class. Right? So the circle class corresponds to positive values of the discriminant, and the cross class to negative values of the discriminant. And so it's particularly for discriminant functions, but also in general, contour plots are pretty useful to be able to read. One other bit of intuition about these is that you can see where the function is steep, right? Here, where the contour lines are spaced close together, the function is steep because you're crossing a lot of contour lines as you move along it. And then let's say, you know, maybe over here, right, it's slightly less steep because the contour lines are farther apart. And over here, it's really flat because you only cross one contour line in a long distance. Another thing that is maybe nice, if you want to head directly uphill, you head directly across, which is to say orthogonal to the contour lines. So this direction is uphill here. This direction is uphill here, right? And then this direction is directly downhill because I'm heading in towards directions of lower ones. If we go this way, that's directly uphill. And then over here, directly uphill, right? So if we want to go uphill here, we're going to follow a path kind of like that, right? And so you can sort of see how to go uphill and downhill on the function from the contour lines as well. All right. So the next thing that I wanted to say is specifically linear functions, right? So we're looking at linear discriminant functions that are this form, w dot x minus b. Let's look first just at plain, without the intercept term, w dot x discriminant functions. And so the decision boundary is going to be the level set of this linear function, right? It's the zero level set of this linear function. And it's going to be a hyperplane, right? Here it's just a line in 2 dimensions, but in general, in n dimensions, it'll be an n-1 dimensional hyperplane. And you can see here that w, this parameter we're trying to learn, is the normal to this, to p sub w, this hyperplane, right? And so that geometric interpretation of the line is important to keep in mind, that by specifying this parameter w, you're specifying the normal to the hyperplane. All right. And if you go back to a full contour plot, again here, it's the normal to this hyperplane, the zero contour, but it's also the direction of steepest increase, which is to say the gradient of our discriminant function. All right, and the length of w, we can scale w up and down, and it doesn't affect this plane, but obviously it would make this, this function steeper if we scaled w up, and less steep if we scaled w down. All right, so now we can shift the plane so that it no longer goes through the origin, right? So if we have x such that f sub wb of x equals 0, that's a plane that doesn't go through the origin, and it looks like a plot that I'm going to draw on the slides in just a sec. But before we go there, I want to go through go through these properties, right? So the vector w is still the normal to the hyperplane, and this intercept parameter b now shifts the plane forward or backward along the direction of w, right? So if we change b, if we set b equal to 0, the plane that we're talking about, p sub wb, will go through the origin, and if we change p, we'll shift the plane forward or backward. If we scale w and b at the same time, it doesn't change the plane, but if we scale them separately, then we can change the plane, and here are some qualitative statements about how the plane changes. So if we scale up b, if we make it bigger, it moves the plane farther away from the origin. Similarly, scaling down b, multiplying by a number less than 1, moves the plane closer to the origin. Scaling w has the reverse behavior, right? So making w bigger moves the plane closer to the origin, and making it smaller moves it farther away from the origin. Flipping the sign of either w or b will flip the plane to be on the opposite side of the origin. and flipping the signs of both w and b. Remember, scaling doesn't matter, so if we scale both of them by -1, it doesn't matter. It doesn't change p of wb at all, but it does change the discriminant function f sub wb, and in particular it flips which side of the plane corresponds to positive values of the discriminant function. All right? So now let me switch back to our slides. Let me get myself a blank slide here, and I'll start doing some sketches of some hyperplanes, right? So we're looking at the plane w dot x minus b. And so let's take a vector w, right? And so this is the vector, let's say 2, 1 equals w, right? And then if we set, I'm going to continue this axis here so that we can keep drawing. And so if we set b equals 0, right, we'll get the plane that goes through the origin. And again, w is the plane's normal, and so we'll get the plane that's normal to w and passing through the origin. Right? Now let's suppose that we set b equals 1, right? So there's a nice little trick to figure out where the plane is. So since the plane is normal to w, it's always going to pass through the vector w somewhere, right? And so we'll get some point, it'll pass through the point x equals k times w for some real number k, right? So let's solve then. W dot x, which is kw, minus b equals 0, right? And so then this term here, this is k times w dot w. W dot w is the norm of w squared. And we'll just move the b over to the other side, right? And so we'll get the norm, we'll get that k is equal to b over the norm of w squared, right? And then that means that x, which is equal to k times w, right, will be, so we'll just write out k. I'm going to split up the w squared into two terms. So we'll get w over norm of w times b over norm of w, right? And so here, right, this is a unit vector, a vector of unit norm in direction of w. And this here is distance that we move from the origin. Right? So here, the length of w here is square root 5, so a little bit over 2, right? So a unit vector, right, I'm going to write here that this is w over norm of w, right? And so, right, so here we go, norm of w squared is equal to 2 squared plus 1 squared, which is 5, right? And so if we set b equals 1, that means that we're going to move a distance 1 over the norm of w away from the origin, right? And so about 1 over 2.2, so maybe 0.4, right? So here, like this, right, this is going to be b equals 1, right? And if we set b equal minus 1, we'll move the opposite direction, but the same distance, right? And then if we were to scale up w, right, that means that the distance we move scales down. And so let's say we doubled w, right, then we would, this is the b equals 1 plane, but it's also the plane we would get if we took b equals 2 and w equals 2w. I'm going to make that an assignment to make it clear that w does not equal 2w in the sense of an equation. All right, so hopefully, hopefully this gives you some more intuition. It's again, since we talk a lot about discriminant functions, and in particular linear discriminant functions in machine learning, it's a good idea to get a quick intuition about what the decision boundary looks like, what the hyperplane looks like when we specify it in this form, right? w dot x minus b equals 0. All right, so now let's go and we're going to start working on some in-class exercises. Again, I made a post on Piazza with all of the links that you need to accomplish these exercises. So here's we'll start with a warm-up problem. No need to submit this one. But what we would like is, here's an axis, right? And here's the point 1, 0, and here's the point 0, 2. Oh, I'm sorry, before we do this, let's go back and take a look. People had questions about the exercises. People are wondering about this vector w over norm of w, right? So I guess w over norm of w, this is a vector that's in the same direction as w, right? Because we're just multiplying it by a scalar, 1 over norm of w. And we've multiplied it by 1 over the norm of w, which means that the norm of the vector w over norm of w, well, one nice property of the norm is that the norm of k times w is equal to the absolute value of k times the norm of w, right? So if we just use that here, this is equal to 1 over the norm of w, right? This is positive, so no need to take the absolute value, times the norm of w, which is equal to 1, right? So w over the norm of w, that's a unit vector, a vector of unit norm, that's pointing in the same direction as w because we've scaled w down here by multiplying it by a number less than 1. Okay, so hopefully that is helpful for people. All right, so now let's go back to the warm-up exercise. People are asking whether if you audit the class, do you still need to register on Gradescope or Replit or any of these other services? Yes, if you're auditing, you still need to do at least some of the in-class exercises and lecture notes exercises. The description of the audit requirements is on Piazza. If you click on the Resources tab, then down at the bottom left is a link to the audit question, policies. And so the requirements on auditors are described on Piazza in some detail, but basically they are that you have to get at least the equivalent of a B- grade on the combination of the in-class exercises and lecture notes exercises. So that means that you can skip some of them, but you have to hand in a decent fraction of them and do well on that fraction. Or you have to do not as well and hand in more of them. All right, so here's the warm-up problem again. We have these 2 points, 1, 0, and 0, 2, and we would like to get a line that passes through both of these, and that's in the form, this line here is in the form w dot x minus b equals 0, and we are asking you to figure out w and b so that this happens. And you don't need to hand this in, but I'll wait a few minutes and people can ask questions. And we will try and answer them. All right, so we're back now. So let's go ahead and show the solution to this exercise. So we would like a w with the following properties, right? We would like that w dot 0, 2 is the same as w dot 1, 0, right? And this should be, well, you can see that these 2 points, this one is non-zero only in the second coordinate, this one only in the first coordinate. So we can do that actually pretty easily. If we set w equals 2, 1, then w dot 0, 2 is 2 times 1 is 2. And w dot 1, 0 is 1 times 2 is 2, right? And then we would like w dot x minus b to be 0. And so if we set b is equal to 2, then w dot x is 2 minus 2 is 0, right? And so we can draw it. Here is, right, a function, there's that. And here's w. And to the limits of my drawing ability, this is orthogonal there. And this represents the line that we want. So hopefully that was not too difficult. And again, as always, let us know if you have questions. So now let's get to the actual in-class exercises. And I'll go over them one at a time and give a few minutes for people to ask questions about each one before I move on to the next. And so I'll try to go over them quickly, so don't worry if you can't finish them as quickly as I go over them. I'll leave some time at the end of class for people to look at these. All right. So now what we'd like you to do is sketch, just like I did on the previous plots, sketch yourself a couple of different lines. So here's a vector w minus 1 comma 3. Sketch the vector w itself as well as the lines w dot x equals b for these 4 different values of b. Sketch them all on the same set of axes and clearly label them. And then do the same thing for this other vector, w equals 1 minus 3, which is the negative of that vector. But this one should be on a separate set of axes. So you'll make 2 plots. Sketch them by hand. This is not something that we want you to write a program for. We want you to be able to, by hand, sketch these things to get an intuition for them. And you can just do them by hand, scan them with your cell phone, for example, and upload them to Gradescope. So I'll wait a few minutes for people to ask questions about this one and then move to the next exercise. So I'm hearing from people that the Gradescope link that we posted doesn't work. I think, so we'll try and post an updated link on Piazza, but the TAs are telling me that if you just go to gradescope.com and then click on the class and then click on the assignment is the one that has today's date in the name, then you should be fine. Sorry about the problem. All right, so let's talk now about the next exercise. So we have so the exercise is we would like you to make a contour plot of a given function. And so the description of the function is given here, right? X squared plus y squared plus cosine of 5 times x plus 2y. And you want to make it over the range of x and y in the square that goes from -2 to 2 in each direction. And here you are welcome to use any tool that you're comfortable with. For example, MATLAB or IPython, which we posted some information about how to install on Piazza. We also, in the Piazza post for today's lecture, if you don't have anything appropriate installed, I just want to give you a tool that you can use. So let me show you what that tool looks like. So if you follow the link that I gave to this Replit project, you don't have to read the code at all. It's just a bunch of JavaScript. If you hit run, then over on the right-hand side, you will shortly see a box that you can enter plot data into. And there's some plot data already here, or you can make your own. And if you click Plot Me, then it will come up with a nice contour plot that looks like this. And so you don't have to use this. This is just for anyone who doesn't happen to have a contour plotting tool already installed. This might be the fastest way to make a contour plot. If you do happen to have, say, MATLAB installed, then MATLAB is probably a much better tool. But we wanted to make sure everybody had a tool that they could use. So let's get rid of this. And we'll go back to the description of the exercise. And again, we'll wait a few minutes for people to have a brief look at this and ask questions, and then I will show you the next exercise. All right, we've gotten a question about what is the meaning of this notation. So that notation means this. If we make an axis and we plot the range, this is the range y equals -2 to 2, and this is the range x equals -2 to 2. We're talking about this square here. Right, so you want to make a contour plot that covers this entire interval. So people are asking what to include in the Gradescope submission. All three questions today are going to be just a plot, or perhaps more than one plot, but you hand in only the plot. You don't need to hand in code or anything else. I'm going to go and say the same thing for here. All right, we're getting more questions about the first exercise. So this one right here. Actually, we're getting questions about the warm-up problem. So why does W equal 2, 1? So the answer is that we want to pick any value of W such that these two things, W.02 and W.10, are the same. They could be the same being 2, they could both be 5, they could both be a million. But as long as they're both the same, then we're going to be able to make a line that goes through that result. So I picked just some small integer values of W that make these things both be equal to 2. The scaling of W here is completely arbitrary, right? You just need to pick a scaling of W and go with it, and then choose B appropriately. As I said before, you can represent the same line with the same line you could represent as W equals 4, 2 and B equals 4, right? You could also represent the same line as W equals -2, -1 and B equals -2, right? So the direction of W is determined by the fact that it has to pass through these 2 points, meaning that it has to have the same dot product with those 2 points. The magnitude of B and the sign of B are determined by how you pick the magnitude and the sign of W. Hopefully that clears things up. If not, please ask some more questions. I should say as well, I forgot to answer this second question. If we now double W, but keep B the same, what point on the x-axis does the line pass through? So here, this is for that part. For this part, we'll answer it down here. So here's another set of axes, again with the point 1, 0 and the point 0, 2. And now let's double W and keep B the same. So let's take this solution and double it, and have W equals 4, 2 and B remains the same at 2, right? So now, when we've doubled w, if you remember, right, so we'll just, it goes, w just keeps going off the top end of that plot. And what will happen is that this line will stay, we've only scaled w, so it's the line is still orthogonal to w. But because we've doubled w, if you remember, it said on the slide that it will scale the line closer to the origin when you double w. So it'll go like that, right? And it'll go half of the way to the origin, right? And so right here, it will pass through the point 1/2, 0. So I'll leave that up for a sec. And then in a sec, I'll move to the problem that we're working on. All right, hi all. So looking at Gradescope, it seems like people are having, it's taking people longer than I was hoping to be able to make these plots. So we're not going to, we're going to extend the due date for these exercises. So they're no longer going to be due at midnight tonight. We'll post the extended due date on Piazza. But I want to still show you the last exercise and try and take questions for the remainder of the class on it. Let's, here we go. All right, so the last exercise is going to be to make a another contour plot. So again, we only want to hand in the plot. And what we're going to do is I've given you a data set here. And so let me, it's got points, 4 points of the positive class that are at the corners of a big square. And then 2 points for the negative class. I'll write those as circles, right? And they are at 0.25 comma 0 and 0 comma 0.25, right? And so this one here is +1 comma +1. This one here is +1 comma -1 and so forth. All right, and so in previous lecture notes, we've given you the equations for calculating a Fisher discriminant. We'd like you to assume that the distribution has, here we have probability 1/4 on each of these points. And the distribution for the other class has probability 1/2 on each of these 2 points. And we'd like you to calculate the Fisher discriminant, right, which means you're calculating some expectations over these two classes and setting them up as collecting them into the vectors W and B for the Fisher discriminant. We would like you to use this feature transform. So this is the same feature transform we discussed in class. It's just the set of all quadratic functions that you can form of the two variables. And we'd like you to make a contour plot of the resulting discriminant function, right? So again, this is just the simplest form of Fisher linear discriminant, except for the fact that we're doing a feature transform from R2 to R5, right? And we'd like you to make a contour plot of the resulting discriminant function and hand that in on Gradescope. And like I just said, we're going to, it seems to be taking people a little bit longer to do these exercises than I had hoped. I think it's probably just the difficulty of using new software tools. So we're going to extend the due date. They're not going to be due tonight, and we'll post the new due date on Piazza. All right, so we'll wait around for another few minutes and try and answer questions. Oh, and people are asking us to post a link to the questions on Piazza. Of course, I will definitely do that. They will be in the it will be in the linked from the syllabus. In particular, I'm going to post the scans of the whiteboard the way I always do, and so you'll be able to look at the questions in the whiteboard captures. And I think we're basically out of lecture time. So please continue to ask questions on Piazza and to the TAs. As I mentioned on Monday, I actually have to leave to catch a plane, and so there's no office hours for me immediately after class today. But of course, I will continue to try and answer questions on Piazza, and the TAs have office hours as well. All right. Thanks a lot, everybody.